Highlight grouping. That's what we're going to call this next strategy. The grouping strategy often gets confused with the identical object strategy. The identical object strategy is when there are things that are the same. The grouping strategy is when there are things that are different, but you want to put them together in groups because maybe they hold some similar characteristics. I know this. So you've got objects grouped together. We're going to go through the first example, then we're going to come back to this explanation and show how it looks. Okay? So I know this probably happens to most of you at home with your math books. You're wondering how you're going to arrange them on your shelf. And you've got your calculus books, your algebra books, your geometry books. And they're all different because it doesn't make sense to have 5 calculus books that are all the same. So you have 5 different books of each kind, but you do want to put the different subjects together. Maybe you do this with something else. Maybe you have a DVD collection and you want all the action-adventure ones together and all your cartoons from when you were young together and your special edition Teletubbies copies all on their own. You know, those kind of things. Maybe that's more realistic than the math textbooks. But the idea is you want calculus books together, algebra books together, geometry books together. And so the first decision you have to make is, am I going to put my calculus books first, my algebra books first, or my geometry books first? So our first main decision is how we're going to put our groups. And we have 3 groups, so if we would go 3 factorial, that will count calculus, algebra, geometry, calculus, geometry, algebra. It'll count all the combinations of just organizing my groups. But then once I decide on organizing my groups, I look at what my first group is. Say my first group is my calculus textbooks. I have 4 of them. Within my calculus books, I could arrange those in 4 factorial ways. Because it could be book 1, book 2, book 3, book 4, and so on. There would be 4 factorial ways to organize those. Similarly, algebra, how many ways? 5 factorial, because there's 5 in that group, and 5 objects can be arranged in 5 factorial ways. And my geometry, 4 factorial. So you have 4 main decisions to make with a lot of decisions within those and choices within those. So what do we do with our spaces kind of questions? We multiply them in the end. So going back to our first slide, what do we do with the grouping question? We always figure out how many groups we have and arrange those first. Then we look within each group and say how many ways can the objects within that group be arranged, and figure that out and multiply them all together. So we got 5 people, Amy, Bill, Jill, Lee, and Tom. Just before I gave out handouts, I chose names that would take less time to write down. So they're all 3-letter names. And they want to sit on a park bench, and Jill and Bill want to sit together. So this becomes a grouping strategy because Jill and Bill now become a mini group. Yes? They're all 3-letter. Did I say all 4-letter? No. Bill? Yeah, Bill and Jill, though the L's don't take very long to do, so maybe that's why. Yes? Yeah. So because 2 people want to sit together, we think of them as a little mini group. So what we have, Jill and Bill, Amy, Lee, and Tom, these 2 are grouped together. The rest of these are individuals. I'm just going to put a circle around them because one of the tendencies is to think because Jill and Bill are sitting together, the other 3 have to sit together. But that's not true. Can you see that Jill and Bill can sit on the end, or they could sit in the middle together, and the other ones don't have to sit together? So the way that we look at this is even though these are individuals, we have 4 groups to organize. The one group of 2 and the others are all individuals. So our first decision for our number of groups will be 4 factorial for our groups. Some people have trouble imagining a single person as a group. If that's hard for you, you can imagine Jill and Bill being glued together. And you might know some couples like that, that no matter where you see one, you see the other one. And now this is like 4 people. We had, when I was in university, there was a couple that was like this. Her name was Carrie, his name was Derek. We just called them Carrick because they were always together. So if that's the case and that helps you visualize it better, there is 4 factorial ways of arranging those 4 people, because those 2 people are glued together. But now a grouping strategy says you have to look within each of your groups and see if there's any permutations within a group. And Jill and Bill could sit holding left and right hand, or they could sit holding right and left hand. So there is 2 factorial ways that they could be arranged, and they would still be sitting together. For 48 in total. Yes. And we have different permutations if they're sitting on each other's lap. We're going to say that they're just sitting beside each other for now. Yes.
So in question, I guess we'd have to assume that they would sit on the left and right side of each other?
Yes, because it's still asking for how many ways can they be seated. So that is a different arrangement than if they were sitting.
I like Florence because I think it's very popular to sit.
Right, or they could have chicken fights and have them on the shoulders or something. There's all these possibilities. Okay? Now something's in the air, and now Jill and Bill and Lee and Amy, poor Tom, although he gets his revenge in part C. Anyways, we'll get there. Now when we imagine it, Jill and Bill, Lee and Amy, and Tom, these 2 are grouped together, these 2 are grouped together, and Tom's all by himself, but he's still an individual little group. And now for our number of groups, we would have 3 factorial. And for permutations within our groups, there's the Jill and Bill one, which is 2 factorial, and there's the Lee and Amy one, 2 factorial. If you want to include Tom as 1 factorial, that's okay. But 1 factorial is just 1, and it's not going to affect it. So most people don't bother writing that. And here we would have 6 times 2 times 2, 24 ways. Now, during the course of the week, something happens, and, whoops, something happens. I'll just erase this for now. Something happens, and Jill and Bill must not sit together anymore. Okay? We're not going to worry about Lee and Amy, whether they're still sitting together or not, but now we just want to count the total number of ways that Jill and Bill are not together. And this is where we're going to use something, and I've got it in there, that says the not strategy. Because it's kind of hard to sometimes count things where people are not together, because if you start thinking about your spaces, this is where it becomes problematic. How many choices do you have for your first space? Well, anybody could sit on the end. But then how many people can sit here? Well, it could be anybody unless you picked Jill or Bill, because then you can't have Jill or Bill beside them. So you run into a problem by trying to count it with spaces. And in this case, it's hard to try to count it directly. So what we do is something I call the not strategy, when it's easier to count the bad ones. And the bad ones in this case are when Jill and Bill are together, right? And we did that in A. How many ways were there in A to count them together? 48. So if we counted all the permutations, Well, that would just be 5 spaces, 5, 4, 3, 2, 1, 5 factorial over, which would be 120. Well, if there's 120 ways that they could sit down as all the possibilities, and we know that 48 of them are bad, we could just do all of them minus the bad ones and find out that there's 72 ways where people could be sitting on the bench, but Jill and Bill are not sitting together.